Hello. So today we will learn about the hypergeometric distribution. Now before we learn about the hypergeometric distribution, let's set up the learning objectives. Is we will find first we will understand what is a hypergeometric distribution. We will look at a few examples of hypergeometric distribution, and then we will go and derive the expectation of a hypergeometric distribution and just state about the variance of a hypergeometric distribution. Finally, we would look at the graph of the probability mass function of the hypergeometric distribution, and we will also discuss the cases of the binomial distribution and versus the hypergeometric distribution. Now, what is the need to understand hypergeometric distribution? Now, if you recall, when we did the binomial distribution, one of the most important things which we did when we looked at binomial distribution was the following. We said that the trials have to be independent and identically distributed. So, these were two important things. The first thing was independent and the second was identical. In other words, we call them IID, independent and identically distributed. Now, what exactly did we mean by this independent and identically distributed trials, Bernoulli trials? Now, if you recall, when I toss a coin once, I have two outcomes. I assume it's a fair coin, so I have a head. This head is occurring with a probability half, this tail is occurring with a probability half. Now, this is one trial of my Bernoulli experiment. Now, if I repeat this trial, if I repeat this trial, I am going to have two trials of this Bernoulli experiment. So, this is my first trial. The first trial has an outcome which is head or tail, and this can happen with equal probability half and half. Now, this is the first trial and this is the second trial. This is the first trial, this is the second trial. Again, in the second trial, my outcomes are either a head or tail. Again, the probability of a head or tail are the same. Similarly, if I had a tail in my first trial, the second trial again has identical outcomes, head or tail, again with the same probability. Now, I know that trial 2 is independent of trial 1 and the probabilities, the outcomes are the same with identical probabilities. So, hence we developed a Bernoulli, from a Bernoulli trial, we developed the idea of a binomial distribution where I said that if I have n trials and these trials are independent, then we defined a random variable x which was a binomial with parameters n, which is the number of trials, and p, which was the probability of what we called a success, and this probability of success was the same for every trial. Now, let us look at a situation where I do not have independence and identically distributed. So, let us understand what we mean by this. So, let us look at the following example. In a box, I have 4 white balls and 3 black balls. Now, I am sampling without replacement. I repeat, I am sampling without replacement. What do we mean by this? In the first trial, I can either draw a black ball or a white ball. I can draw, there are 7 balls. So, the chance of me getting a black ball is 3 out of 7. The chance of me getting a white ball is 4 out of 7. Now, I do not replace the ball I have already drawn. So, if I had drawn a black ball, I have only 4 white and 2 black balls remaining with me. Similarly, if I have drawn a white, I have 3 white and 3 black balls remaining with me. So, this is I have not replaced the ball in the box. Now, when I have 4 white and 2 black balls, again The outcomes are I can either draw a black ball, but now the chance of me drawing a black ball is not 3 by 7, it is 2 out of 6. Similarly, the chance of me drawing a white ball is 4 out of 6. Now coming to this branch, again I can draw a black ball. The chance of me drawing a black ball is 3 out of 6, whereas the chance of me drawing a white ball is 3 out of 6. So you can see that if I draw a black ball, I have only one black ball remaining and 4 white balls. Here I have 3 white balls and 2 black balls. Here I have again 3 white and 2 black, and here I have 2 white and 3 black balls remaining. Two things which we need to understand is, drawing a black ball here is not independent of what was the result here. It is dependent. You can see that the chance of me drawing a black ball, if I go from this branch, is 2 by 6, whereas here it is 3 by 6. So whether you drew a black ball or a white ball in the first trial actually affects the chance of you drawing a black or a white ball in the second trial. So the first thing is, we have that trials are not independent. Similarly, the probability of a success, if I define success to be the drawing of a black ball, the probability of drawing a black ball was 3 by 7 here, the probability is 2 by 6 here, and it is 3 by 6 here. So it is not the same. So in this case, I cannot model a situation. What is the question I might be expecting here? So if I am going to look at the number of black balls, here you can see that the number of black balls I have drawn along this is 2, along this is 1, along this is 1, and along this is 0. If I am interested in knowing as to what is the total number of black balls I have drawn, I know it can take the value 0, 1 or 2. But then after, to find out the probability, I need to understand what is this distribution. And that's what we are going to discuss now. So if I am going to understand what is, so binomial will not work because I do not have independent and identical distribution. So I need to go to some other distribution, and that is what we refer to as the hypergeometric distribution. For the hypergeometric distribution to work, initially I want to know that I have a population, and this can be divided into 2 and only 2 independent subsets. So I had black and white balls. The experiment must have changing probabilities of success. We have already seen that the chance of drawing a black ball was changing with my trials. And here we need to understand that I am sampling without replacement. So let's understand the hypergeometric distribution. I want to know what is the number of successes out of a total number of items chosen. So for example, I am going to look at a situation where I have n, capital N represents my population, of which I have m, which is my number of black balls. In my example, this capital N was 7. The number of black balls were 3. Number of white balls was 7 minus 3, which was 4. This was how my problem was. I sample 2 balls, okay, from the population. So that is what I did. So first I sampled 1 ball, then I sampled another ball. So this is how I sampled 2 balls. Out of these 2 balls, I again have a mixture of black balls and white balls. So if you can see, in this I had 2 black balls, in this I had 1 black and 1 white, here I had 1 white and 1 black, and here I had 2 white balls. So I could either have both black, I could have 1 black, or I could have no black. That's what it means. Okay. So this x, in this case, x is the number of black balls. So here I can see that the x is 2, here it is 1, here it is 1, and here it is 0. So, if I am taking x equal to 2, my n minus x is 0, I do not have any 2 minus 2 is 0, I do not have any white balls. Similarly, if x is 1, n minus x is 1, so I have one white ball. If x is 0, I have both 2 minus 0, 2 are white balls. So, the probability mass function of this, so x is called a hypergeometric variable. Now, what are the parameters of this variable? I need to know what is this capital N, which is the size of the population. I need to know what is this M, which is the, I have only two types. So, this is the number of elements of one type. If I know the number of elements of one type, I can find out the number of elements of the other type as just n minus m, and I need to know what is the small n, which is the sample size from this population of capital size capital N. So, in this case, I want to know what is the probability of x equal to x, and then you can see that I am actually the total number of, so the first thing I am doing is I am sampling from, this is my population, this is my sample. I am sampling from this population of size n, I am taking a sample of size small n. And I know this can be achieved in n choose n ways. Now, from this m, I am interested in knowing how many of type 1 is there. So, I am choosing x from here, and this I can do in m choose x ways. Now, I have to choose this remaining n. If I am choosing x of type 1, n minus x is chosen of the second type, and that is chosen. So, I am choosing n minus x, and this is chosen from n minus m, choose n minus x ways. So, you can see that the chance of me having x equal to x, this is my total ways of choosing the sample of size n from a population of size n, that is n choose n. X is chosen from m in m choose x ways, and n minus x is chosen from n in n minus m choose n minus x ways. So, hence this is what we have as the probability mass function of a hypergeometric distribution. Now, what are the values this x can take? For now, I again repeat for now, because I am going to change this very soon, but I am assuming that since I have taken a value of n, x can take these values 0, 1 to n. We will see whether this is a valid condition for all cases. So, now going back to this example, I had in this case x is nothing but BB, this is BW, this is WB, and this is WW. So, the value of x, where x is the number of black balls in my sample of size 2. So, I have x here, I have 2 black balls, here I have 1 black, 1 white, here I have 1 white, 1 black. So, this x takes the value 1 here, here x takes the value 0. So, my random variable takes the value 0, 1 and 2. So, what is the probability with which it takes this value? Now, again if you go to the multiplication rule, I know this is probability of B1, B2, this is B1, W1, this is W1, B1 and W1, W2. So, this is probability of B1 into probability of B2 given B1. Probability of B1 is 3 by 7, B2 given B1 is 2 by 6. So, this is a 6 by 42. Now, this is going to be 3 by 7 into 4 by 6. This is 4 by 7 into 3 by 6. So, the chance of this happening is going to be 24 by 42, and this is going to be 4 by 7 into 3 by 6, which is 12 by 42. So, x equal to 0 is with a probability x equal to I with the probability 6 by 42. This is 24 by 42, this is 12 by 42. I can verify that this is a probability mass function. 24 plus 6 is 30, 30 plus 12 is 42. This adds up to 1 and all of them are greater than or equal to 0. Now, if I apply the formula, so in this case I have n equal to 7, small n equal to 2 and m equal to 3. So, probability of x takes the value 0, 1 and 2, x equal to 0 is going to be 3, choose 0, into 4, choose 2, divided by 7, choose 2, okay, because this is my capital N, I am just applying the formula which is going to be 3 factorial by 0 factorial into 3 minus 0 factorial. So, this is going to be just 1. 4 factorial by 2 factorial, 2 factorial, 7 factorial by 2 factorial, 5 factorial. So, I can cancel out this. I have a 4 into 3 and 3, this is cancelled out, to 7 into 6. So, this is going to be a 12 by 42, which is what I have here. Now, if I look at x equal to 1, I have a 3, choose 1, into 4, choose 1, the denominator remains the same, 7, choose 2, 3, choose 1 is going to be 3 factorial by 1 factorial, 2 factorial, 4 factorial by 1 factorial, 3 factorial by 7 factorial, divided by 2 factorial, 5 factorial, which is going to be a 3 into 4 from here. So, I will get a 3 into 4 divided by 7 into 6 into 2, which is 24 by 42. The last case where x equal to 2 is going to be 3, choose 2, 4, choose 0, divided by 7, choose 2, 3, choose 2 is 3 factorial by 2 factorial, 1 factorial, 4, choose 0 is 4 factorial, 0 factorial into 4 factorial, and I have this. So, I just have a 3 into 2 divided by 7 into 6, which is a 6 divided by 42. This is precisely what we got earlier also, and we can verify that this is a probability mass function. So, the key point to notice is when we talk about a hypergeometric distribution, we need two things. One is my trials are not independent and the probability of success is not the same for each trial. Now, let us look at a few more examples where we are choosing where the hypergeometric distribution can be applied. Now, I have a bag consisting of 50 balls, 30 are white and 20 are blue. So, again if I go back to my framework, I know I have this capital N which is 50, 30 are of one type, 20 are of another type. Now, my M and N would depend on what is the distribution I am seeking here. I am seeking X to be the number of blue balls. So, my M equal to 20 and my N minus M equal to 30. Okay, my M equal to 20. Now, the student samples 5 balls. So, my N equal to 5 and this is without replacement. So, now what are the values this X can take from? So, I can have in my sample no blue balls, 1 blue ball, all the 2 blue balls, 3, 4 and 5. Okay, because M equal to 20, number of blue balls are 20. I can have all these values and I know from my probability mass function, the probability of X equal to I is nothing but M choose I, N minus M choose N minus I into N choose N. So, this is a general way of writing the probability mass function for values I equal to 0, 1, 2, 3, 4 and 5, and you can verify that this all of them are greater than 0 and the sum adds up to 1, saying that this is a valid probability mass function. Now, let us look at another situation. For example, if I am looking at a population in a particular locality which has 150 female voters and 250 male voters. Again, my population size here is 400, which is just the sum of the number of m and n minus m. Again, I have female which is 150, I have male which is 250, and I am choosing a group of 25. So, my small n is 25 in this case. What am I interested in knowing? That I am interested in knowing, so here x is the number of female voters in my sample. I am choosing 25. If x is the number of female voters in my sample, my small m equal to 150, my capital N minus m equal to 250. So, I am interested in knowing my m is 150, n is 25, capital N is 400. I am interested in knowing probability, the number of female voters in my sample is equal to 10. That is what I am interested in knowing, and I know that is equal to m choose 10, which is 150 choose 10 into n minus m, which is 250 choose n minus 10, which is 25 minus 10, which is 15, n choose n, which is 400 choose 25. So, this is my n choose n, this is my m choose 10, this is my n minus m choose n minus 10. So, that is how I get the probability that 10 of the selected voters would be female. And why is it a hypergeometric distribution? Because if I choose one female voter, one voter, and I see that person is already a female, I cannot add that person again. I need to remove that person from the sample, and hence it is a sampling without replacement. Now, let us look at a case where I have a batch of 10 computer parts. It is known that there are 3 defective parts. Again, what are the 2 types here? I have a population of 10 parts. I know that there are going to be 3 which are defective. So, 7 would be non-defective. I am selecting 4 of the parts at random. So, this is my capital N, this is my small n. I am defining the random variable to be the number working. So, what is the number working here? So, here my m equal to 7 and my n minus m is equal to 3. So, I have non-defective and defective. From this I am choosing a sample of 4 and I want to know what is the values this x can take. So, x equal to 0 cannot happen because I have only 3 defective. So, I cannot have a case where I have all the 4 defective. X equal to 1 would imply that I have 1 non-defective and 3 defective. This can happen. X equal to 2 would imply I have 2 non-defective and 2 defectives. This can also happen. X equal to 3 would imply I have 3 non-defective and 1 defective. This can also happen. And x equal to 4 says that I have 4 non-defectives, which can also happen. So, the values this x can take are 1, 2, 3 and 4. Again, x equal to 0 cannot be possible because in that case this would become 3, 4, which is not possible. So, you can see that it is very important for us to understand what are the values this x can take. So, x can take a minimum. So, that is something which we need to understand. So, here x takes the values of 1, 2, 3 and 4 and the PMF, this is the range of values x can take, x cannot take the value 0. Now, suppose I flip it, instead of instead of defining the random variable to be the number of non-defective computer parts, if I flip it and I ask that suppose x is the number of defective computer parts, in which case my m equal to 3 and n minus m is equal to 7. Again, what is x? X is the number of defective computer parts chosen in this sample. Now, x can take a value 0, x can take a value 1, x can take a value 2, x can take a value 3, but x cannot take the value 4 because I have only 3 defective parts. So, x cannot take a value 4 in this case. So, the values x can take are only 0, 1, 2 and 3. X takes the value 0 would imply that I have all which are non-defective. X takes the value 1 would imply I have 3 non-defective and 1 defective. Here this would imply that I have 2 non-defective and 2 defective. Here I have 1 non-defective and 3 defective. This would imply that I have all 4 defective. This case cannot happen because I have only totally 3 defective parts. So, x cannot take the value 0 and I have only the range of values x can take is 0, 1, 2 and 3. So, again what we can see is if x is starting from a value of 0, x is taking a value which is minimum of n and m. The minimum of n and m in this case is 4 and 3. So, x was taking a value which is going to be 3. Okay. This is the range. So, x takes the value 0, 1, 2 and 3. Now, suppose we sample from a deck of cards. Again, I take a deck of 52 cards. I am drawing 5 cards from this deck. So, again to relate it, I have n which is 52. This is the size of my population. I am drawing from this 5 cards. So, my small n is equal to 5. Now, I am denoting here x is the number of aces in the random sample of 5 cards. Now, in my population, I know that in my population, how many aces do I have? I have 4 aces and I have 48 non-aces. 4 are aces and 48 are non-aces. So, my m is 4 and this is my n minus m. And my x is denoting the number of aces in this random sample. So, you can see that n is 52 which I have here, small n is 5 and m equal to 4. Now, what are the values this x can take? I know that the maximum value x can take is I can have no ace, I can have 1 ace, I can have 2 ace, I can have 3 ace, I can have 4 ace, but I cannot have the value 5. Again, x takes the value which is minimum of n and m, n equal to 5, m equal to 4. So, x takes the value 0, 1, 2, 3 and 4 with the probability mass function which is m choose x. This is n minus m choose 5 minus x and this is n choose n. So, this is what we need to understand is in general I can state that the probability mass function of a hypergeometric distribution. So, if x is a hypergeometric distribution with parameters capital N, small m and small n, where capital N is the size of my population, m is the number of units in the population which are of one particular type. I am assuming only 2 types, and small n is the size of my sample. Then the probability x takes a particular value, x is m choose x, n minus m choose n minus x to n in n, where x is less than or equal to n or m, which can be written as x is minimum of m and n minus x should be less than or equal to n minus x for this to happen, and that is x is greater or equal to m plus n minus n. So, it is either the minimum of mn or the maximum of m plus n and n. So, it should be greater or equal to 0. Hence, I know that m plus n should be greater or equal to n. So, this is what I refer to as the probability mass function of the hypergeometric random variable. What is the hypergeometric distribution? The two key aspects that are different from a binomial distribution are, here my trials are not independent and not identically distributed. So, I have basically this arising because I am doing sampling without replacement. And I obtain the probability. So, I have a hypergeometric distribution which has parameters capital N, small m and small n, and the probability x equal to x is m choose x, n minus m choose n minus x divided by n choose n, where x is less than or equal to minimum of m n and x should be greater or equal to m plus n minus n. These are the conditions for the values x can